So I'm Clifford. I lead the team at Google Munich in Germany that works on V8, which is a JavaScript engine you might have heard of that is used both in Google Chrome and in Node.js. So I'm going to ask for a little bit of audience participation here. Who has actually written JavaScript on the client side? Well, that's good. All right. Server side? Wow. All right. Good. Who's actually heard of V8? All right. So that's good. All right. Good. So before I get into the actual meat of my talk, I'd like to sort of set the frame for the discussion and the topics that I'd like to share with you today. And it's a little bit of a cautionary tale. So I've been in this industry for more than 25 years. And I've seen a lot of dreams come true. And not all of those dreams have worked out quite the way you expected. And so the quote that I'd like to share with you to start out with is, beware of what you're wishing for in your youth, because you may get it in your middle age. So this quote actually is attributed to a relatively famous, sometimes lyric poet and philosopher and statesman, Johann Wolfgang von Goethe. And it's kind of attributed as the source of a little bit more common phrase that you may have heard of as well, which is, be careful what you wish for in life because it might come true. And the reason I give that context right now is it turns out that a significantly less well-known philosopher and not very talented writer actually had a quote that is very applicable in our space as software developers and sort of and product and developers of complex systems. And that goes something like this: be careful what you optimize because it might get faster and nothing else. So keep that in mind as sort of the frame for the discussion I'd like to have today with you. And with that, I'd like to show you my overview. It's an overview. I'd like to start out with, it's funny. I'd like to start out with something that I make it sound really official, called the synthetic benchmark dilemma. This is how benchmarks can go bad. I'd like to talk to you a little bit about how V8 works and how that's changed over the last couple of years especially, because it gives a frame for how the lessons that we've learned over the last couple of years. And I think there's actually lessons here that are applicable to development of any large software system. The lessons learned, of course, are an important part of this. And what I'd like to sort of focus on is this thing called self-hosted versus optimized built-ins. And I'll get into what that is, so don't worry about it at this point. And the last thing I'd like to do is tell you about what we did once we figured out that the lesson we had learned was important. We did something about it, and this is this section called Building a Builder Built-in and the Code Stub Assembler. So let's get into it. The synthetic benchmark dilemma. I'd like to take a little walk down memory lane here. V8's been around for a while now. When it first came out, when Chrome was first released, the benchmarks that were used to test JavaScript speed were what we now, in retrospect, call micro-benchmarks. So SunSpider, Kraken, they were useful at the time because they tested certain key functionality of the JavaScript runtime, which was important for small applications to have run quickly. As applications grew bigger, and V8 was responsible for part of this, that applications could become more complex. The type of things that needed to be tested for in benchmarks also became bigger. So around 2012, or in 2012, we released a benchmark called Octane, and it tried to represent a broader spectrum of use cases that we could optimize for, so that we would do a better job of actually optimizing for the applications that we find in the wild. It turns out that we haven't quite gotten it right. V8 did a really good job of optimizing the benchmarks that we had, so SunSpider, Kraken, Octane. But at some point we realized that those benchmarks didn't really reflect what was going on in the wild. And so we created an internal benchmark where we took common websites and we ran them through some automation that we built, and we measured exactly where they were spending their time. And there were some interesting results that came out of this. So this looks really complicated. and you don't have to understand all the details here, but what I'd like to point out is on the left-hand side is a list of a bunch of websites, and probably difficult to read from way in the back row, but some of those might look familiar to you. And each of these bars next to the website is a distribution of time, what Chrome is actually doing when you're loading that website. And we created these tests so that we could run them again and again, we'd be able to do optimizations, and see how these profiles would change. The thing to notice here is on the bottom, there's a legend, and you'll see that the time that we spent on websites was really kind of across the board. We spent some time in JavaScript, but we also spent time in callbacks. That's Blink, that's in the DOM, for example. We also spent time parsing. I'll get back to that, or I'll show that where that fits in later. And there was various other things that we were doing when we were loading the websites. Now, the interesting thing here is you see that every website is a little bit different, but you do see some patterns here, or at least one pattern that was very interesting to us, and that is the pinkish bar on the right is relatively small. It's 25% or less on all of the websites that we tested. And that came as a surprise because that's the JavaScript piece. That's the time spent actually executing JavaScript. And why is this interesting? Well, if you take a look at Octane, the benchmark we came out with in 2012, look where Octane spends its time, right? It's almost all pink, or 2/3, 3/4 pink, which means what we were optimizing for many years was not actually representative of what is out there in the web. Okay, so that's something we need to fix. And over the last couple of years, we've been working hard to fix that. And the way we've done this is try to look more at real websites, and on the server side at Node.js performance and real applications, so that we can tune V8 for the type of workloads that we'll typically see in the wild, and not just the ones we see in benchmarks. Fortunately, there are a couple of benchmarks that are now more representative of these workloads that we'd like to optimize for, that you see in real-world websites. There's Speedometer, which simulates a MVC to-do app with a bunch of standard JavaScript frameworks, and we can test and see how long Chrome and V8 need in various parts of these semi-realistic applications. And there's also Aries6, which is a benchmark that tests newest ECMAScript features, so ES6 features. You'll see that over the last couple of years, we've gotten a lot faster with V8 in these workloads. That's really good news, because this translates directly to the type of performance that you would want to see in your website and on the server side in Node.js. One really important lesson out of all of this is that what we realized is that if you have a benchmark that optimizes for something specific, or that shows a specific problem, you will end up optimizing for that problem. And that can become a little bit of a trap, because optimization's fun. We enjoy doing it on the V8 team. But if you have the wrong goal, you will continue to pursue that goal unless you know when you're done. And you may run the risk of ignoring other things in the process. Specifically, what we realized, and you saw that in those graphs before, is that the performance profile of most apps out there is all across the board. There's time spent in JavaScript, parsing, DOM, lots of different places. And if you're just specifically optimizing for one of those slices, then you risk not having a platform that is consistently performant. So there's this concept of a consistent baseline performance, which is sort of a mantra that we've had over the last couple of years, to make sure that not just specific use cases are fast, but that JavaScript and the web platform and Node.js is fast across the board. Make sense? Okay. Breathe. So with that in mind, I'd like to talk a little bit about how V8 works and how we've changed it over the last couple of years with this new focus on real-world performance. Two technologies I'd like to highlight going into this discussion: Ignition and TurboFan. We've spent the last couple of years building fundamental new technologies into V8 that make it faster in the real world and across a broader spectrum of use cases. The first one is the Ignition interpreter. The Ignition interpreter gives us the baseline performance, the consistent baseline performance we need if we're running all sorts of different JavaScript. We have the TurboFan optimizing compiler, which takes a look at the most commonly or the most frequently executed pieces of code and then optimizes those selectively. With these two new components, we're able to address a much wider set of use cases than we did before. I won't dwell into all the details of what we used to do in V8, but as of Chrome 59, so that's almost about a year now, these two technologies are the primary ones in V8 that allow us to address the performance needs of a broad set of use cases. Okay, let's talk a little bit about how V8 uses these two technologies, Ignition and TurboFan, and integrates them into its pipeline. This is a useful model, also thinking back to that set of graphs that I showed, where the distribution of times in the different bars. This will kind of show you where those come from, or some of them come from. So how does V8 work? Well, we take your JavaScript code, and it goes through a parser. And that parser turns it into an abstract syntax tree. This is kind of standard computer sciencey stuff. And then that abstract tree, syntax tree, gets turned into interpreter bytecode. That's the interpreter bytecode that gets run through Ignition, which I mentioned on the previous slide. As we're running that code through the interpreter, we're not just executing. We're looking for signals from the executing code that we can use for later optimization. JavaScript's kind of a tricky language. It's pretty much on type. It's the Wild West. Yeah? You can create a variable. One time it's an integer. Next time it's a string. Next time it's an object. And there's really no signals to V8 beforehand what you want, what your intent is. Or there are a few signals. I'll actually get into that a little bit more. So without those explicit types that you would find in other language, V8 has to actually learn a little bit about your code on the fly before it can make it faster. So what the interpreter does is it runs your bytecode for a while, collects feedback. We call this type feedback. And with that feedback, it then sends the hottest pieces of JavaScript code to the TurboFan compiler, where your JavaScript gets optimized, selectively turned into machine code that runs really fast. So a couple of high-level observations about this new system and why it's actually better than what we did before. I'll go back to this. This looks complicated. It's actually pretty simple. You notice that there are arrows here. We go from one stage to the next. There are a couple exceptions that I won't go into here, but the idea is that we can reason about the system because the units are self-contained and the interfaces between them are relatively well-defined. It wasn't always the case in V8 that it was quite that clean, and it has helped us have some important important attributes to the runtime. First of all, both Ignition and TurboFan support the entire JavaScript language. Before these technologies were shipped, it wasn't the case that we could optimize all the JavaScript. The one story that many of you or some of you may know of is that try-catch, so exceptions, structured exception handling, was not optimized in older versions of V8. It would be a problem because it limited, with only a selective set of language functionality being optimized, it limited what you could do as a developer and what you could rely on to be fast in your applications. So now, TurboFan and Ignition optimize the entire JavaScript language. They provide consistent performance. I mentioned the consistent baseline performance as a sort of a mantra. We believe that with these two technologies, we've solved a couple of the interesting problems that we used to have that allow us to give you soft guarantees about the baseline performance of your code. And I mentioned simple before. I know that picture with the flow of information through V8 looked like a lot of little boxes, but it used to be that there were arrows between those boxes that were sort of unintuitive and difficult to reason about. So with this new system, we were able to create something that was simpler and more comprehensive than the compiler and the compilers that we had before. Now, this is something that will become important in the discussion we have later. Simplicity, and this is one of the takeaways that I'll mention at the end, is simplicity can be your friend because if you invest too much in complexity up front, then that complexity is something you pay for over time again and again. If you create a simple system at the beginning, it's easy to reason about, it's easy to measure, it's easy to actually identify problems with and fix bugs with and to maintain. So despite all the complicated stuff that's going on in V8, it's sort of a design goal that we have to keep things as simple as possible. necessary complexity, but only the necessary complexity. Because a simpler system is just simpler to reason about, simpler to fix. And as you build a complex system and it gets bigger and bigger, without that simplicity, at some point, you're just lost. You can no longer move. I talked about feedback and how we generate or how we optimize code in V8 based on the feedback we generate. So I'd like to go into a little bit of depth about how this is done, because for my later examples, understanding this turns out to be important. We use this mechanism called inline caches. Anybody ever learned or heard of inline caches here? Oh, okay. Oh, wow. One. That's excellent. So inline caches. So this is good that I talk about this. Inline caches are a mechanism that we use to make operations faster, both in the interpreter and to record type feedback or information that is necessary for later optimization in TurboFan. And I'd like to give you an example of how this works. So this is a very simple function here that either returns the first element of an array or undefined, depending on the size of the array. I think this is pretty straightforward code to understand. As you send this code through that pipeline that I outlined before, it first generates bytecode. And this is what the bytecode looks like. So don't sweat the details of the bytecode. This looks very sort of assembly language-ish. It kind of is. And I'll get into what is important here in a few minutes. Now, when we create the bytecode, we also build it such that we can collect information about it as it runs. And there's this thing called the feedback vector, which is sort of comes hand in hand with the bytecode. And to orient you a little bit, I'd like to show how these three pieces sort of fit together. So you'll see that the first thing we do in the function is ask for the length of the array. And from that, or from that statement, we generate a bytecode in the interpreter, which is also highlighted here, called a LDA name property. Load the accumulator with a named property. Don't sweat the details here again, but you'll notice that the 0 in the bracket at the end actually refers to the last one, to an index in this feedback vector. And these highlighted portions of the code here on this slide all sort of belong together, as do these here. So the equality operator here, turns out it's JavaScript, so we don't actually know beforehand the exact details of how the equality operator needs to work at runtime, depending on the types that you send it. So we have to collect feedback on that as well. So for that, we have a bytecode, and we have a slot in the feedback vector to hold the information as we gather it. So the last operation we have is in the case that the array is not empty, we load the first element out of it. And again, this is a bytecode that refers to slots in the feedback vector, so that as we execute it, we can learn and get better. Make sense? Okay, so let's see how this actually works at execution time. Let's call that routine that we just with an array of integer values. And as we go through, I'm going to focus just on the bytecodes that fill in type feedback. As we go through, we take a look at what was actually passed to the interpreter for particular operations. In this case, when you start the function, you ask for its length, the length of the array that you passed in. We get that property from the array object. The first time we see it, we inside of V8, and again, don't sweat the details about what these things are called, we record, hey, this was an array of integers. We have an internal term that we use called map in V8. It's kind of a fancy or not so fancy word for sort of the class descriptor or the shape descriptor of the object that it's currently looking at. So in this case, we're looking at an array of integers. We remember in the first slot, we saw an array of integers the first time, and in order to do that operation on that array of integers, there's a handler, it's a code pointer basically, that gets remembered in the feedback vector that we compute at the first time we see this operation. And we store it in the type feedback vector so that later we can come back and execute it quickly or more quickly again the second time. It also serves as a placeholder for later with this by filling in the type by filling in the feedback vector, we know what types we saw, and that can be used as hints to the optimizing compiler. Second operation, the strict equality check. The length was an integer value. So in here, it's a slightly different format in this slot. We just remember it's an integer that we saw. And finally, when we loaded the first element of the array, we remembered the same, or we recorded the same information that we did when we took the length, which is the shape of the object, its map, and we created a handler or assigned a handler to that slot in the feedback vector to say, here's the code that actually will perform that operation given this type. The nice property, after the first time we run through, is that this code is what we call monomorphic. So monomorphic means one shape. For these operations that can do different things depending on the types you pass in, we have only seen one type. And that's a great thing for V8 because the next time around in the interpreter, when we run it, we know what we saw before, and we can make some assumptions about how it's going to work the next time, assuming that it stays the same. And when the optimizing compiler runs later, when TurboFan runs, it can use these assumptions to generate much better code. So this works great for simple code. It gets more complicated when you start introducing different types. So I'm going to call first again, but this time with an array of strings. And it turns out, the way V8 is implemented, that array of strings looks different in the implementation under the hood than the array of numbers did. So let's see what actually happens when we execute this code. The first thing is we execute the load of the length of that array, and because it's shaped differently than the integer array, its map is different, and we have to record this fact. And the way we do that is it no longer fits in line in the feedback vector. We have to allocate a side data structure, and we put both entries in there for the things that we've seen. Right? So we've seen a map, we've seen the shape of an integer array, and we've seen the shape of an object array. So this information has to be stored for later fast execution in the interpreter and for optimization. But you see that it's now become a little more complicated. We already had this out-of-line structure. You can see things are starting to get a little bit more complex. Good news is when we do the equality operator, it's still an integer, so that stays the same. But when we ask for the first element of the array, the shape is different. And again, we have to record that fact. So if you look at the feedback vector after you've made both of these calls, you have different entries than you did when you ran through the first time. Because we've seen different types, that has caused certain operations to go what we call polymorphic, many-shaped. Turns out, this is something that has plagued us over the years. Polymorphic operations and the way we handle polymorphism in V8 directly translates to performance, how really complex systems perform. If we handle polymorphism well, complex systems tend to get better and faster. And this is something that we wrestle with. And that's important for an example that I'd like to show you now. So given that background, kind of know how V8 works, fundamentally how the interpreter works, and how we use the information gathered from type feedback it gets fed into the optimizing compiler. And that polymorphism is something that you have to watch out for because it can actually make your code slower. This became acutely aware, or we became acutely aware of this in the example that I'd like to show you now. Let's say you need a function in your program that sums all of the elements of an array. So here's a function that I wrote by hand using sort of idiomatic ES6. It goes through all of the elements of an array. For the first element, it just remembers it. Otherwise, it adds it to the element that it saw, or the sum that it has collected up to that point. Makes sense. What I did is also wrote a little timing routine here that you can pass the array to, and it wraps that sum function so you can run it over and over again and get some statistically significant performance results and make judgments about how fast things are. Okay, so let's test that routine. Let's see how fast it is in V8. So with that handwritten sum, I create an integer array and run it through my benchmark harness, and 100 milliseconds to run it. I think it was about 1 million times. Okay, that's pretty good. Then I run it again, this time with an array of strings. So maybe this is ringing some bells. There's something going to be different going on here, right? Got slower. Got a lot slower, even though the array is shorter. So there was less work to do, but it got slower. Okay, something's going on there. Finally, I'm going to run it again with the integer array that I passed the first time. Ouch. Now it's really slow. Is this expected? Would you want your program to do this, right? This is not the consistent baseline performance we're hoping for, which is you do something once, you do it again, and you get the same results, both in correctness and in performance. Okay, so what's going on here? Why is this so slow? Anybody? Any guesses? Polymorphism. All right, we talked about why this is kind of a trap that V8 can fall into. You'll notice that in the iteration of the sum function, one of the things that is done is it fetches each of the elements. And we use this construct, this for-of construct, which under the covers does nothing more than sort of that work that I did before, where it looks at the length of the array and it takes the current element that it's on out of the array. It, under the covers, requires the same machinery that we saw in the example that I showed before. And it has the same dangers, the hidden dangers, that if you pass it two arrays of different types, then it generates polymorphism for those operations. It even gets a little more subtle in this than that, because when we sum the elements together, the operator for doing plus in JavaScript wears many hats. And it can be an integer addition, in which case you get integer addition, or it can be string concatenation, which is a little surprising, but it works that way. So the first time we run the sum function with an integer array, we get an integer result, and that plus is an integer operation. The second time, though, just like we saw polymorphism when fetching the elements from the array, when we add the elements out of that array together, the first time they're integer, second time they're strings, we have to have a more complex implementation. It becomes polymorphic. It becomes slower. So this is why the handwritten implementation is slow. Okay. Maybe the V8 team can do this better, right? We have these things called built-ins. If you know JavaScript reasonably well, you know that the prototypes of many of the built-in objects have a whole bunch of utility functions, and those functions are defined in great detail in the ECMAScript spec. If you read through the spec, it says this is exactly what it's going to do when you call for each, or this is exactly what we're going to do when you call array index of. And the good thing about that is that because we have this contract defined by ECMAScript, you'd think that gives the VM implementers, the V8 engineers, a lot of opportunity to make those built-ins faster. Because they get shipped with V8, we can sort of do all the tricks beforehand, and you can benefit by using those built-ins, using all that sort of that we put into those, right? Okay, so turns out there's a built-in for this, and it's the reduce built-in. So this is using ES6 syntax. I got a little arrow function here. I've idiomatically expressed what I was trying to do in the sum function at a little higher level. I've expressed my intent by using the reduce built-in on the array and provided this arrow function to tell it what it should do for each element. So what this sum function in essence does is exactly what the handwritten code does, but it sort of wraps my intent in a language construct, an explicit language statement, which is one of these built-ins of the language that is well-defined and its behavior is well-defined. So you think, wow, this could be faster, right? This is going to be better because the V8 engineers have taken care of this. Well, if you run the same benchmark that I had before, up until Chrome 58, here's what happens. Integer array. Ow, that hurt. Got the result right, though. Run it with strings. Okay, marginally better, but still not great. And a third time through, faster? What's going on here? Okay, that's about almost 5 times slower than doing it by hand. So why would you use a built-in? All that specialty knowledge we have seems to have not helped. It's unfortunate. Why? Well, up until Chrome 58, Many of our built-ins, and specifically this reduce built-in, were what we called self-hosted. It's sort of a seductive idea of when you're building a VM to say, you know what, we're going to build one compiler, we're going to build one interpreter, and if we express everything in terms of JavaScript, no matter what it is, then that interpreter and that optimizing compiler, they'll just take care of it. Right? It won't be our problem because the compiler is smart enough. So the reduce built-in was written like this up until Chrome 58. And you'll see it's considerably longer than the handwritten version. The reason for that is because the ECMAScript specification for this built-in is actually pretty long and has a lot of edge cases, a lot of things that have to be dealt with. And expressing that as JavaScript, there's an impedance mismatch. Anyway, regardless of that it's a little bit longer, you still have fundamentally the same problems. There's polymorphism in this code because it's JavaScript code. If you use self-hosting to represent sort of these really common built-in pieces of functionality, you run the same risks in the built-ins that you would get in your application code. So what's the observation? Don't self-host built-ins. Optimize them. And sort of the observation here is a little deeper than that, and goes back to sort of my original observation at the beginning of the presentation, which is if something's going to be important for performance or anything else, premature optimization, or even sort of building a mental model around something you think you will use later to optimize. In this case, we thought, we're going to have a great compiler. We're going to have a great interpreter. It'll just solve this problem for us. That's pushing off technical debt. That's sort of making assumptions which can come around later and bite you, which they did in this case. So another way to look at this is say, well, if it's really important for performance, why don't we build a solution which is customized for the use case we have? So turns out what we did over the last couple years. I want to talk to you a little bit about how we did that, because I think it's kind of cool. It's a little bit, shows you under the hood what we're actually doing in V8 to make these faster. You might ask, okay, since the built-ins are so commonly used in so many different cases, and we have the specialty knowledge about them, because we're VM engineers and we have this specification, we could do all this work in advance, wouldn't it be great if we had super tight control over what was generated in the built-in? Because in the JavaScript code, there's sort of this abstraction that when we did the self-hosted built-in, we sort of lost information. There was an impedance mismatch. We lost sort of the expression of intent, like this is important to get fast, and maybe use some tricks here. You couldn't do that in the JavaScript self-hosted built-in. If there was a way we could exercise that at a much lower level, that would be great, right? So maybe JavaScript's not the right tool for that. How about we use C++, right? We could implement these built-ins in C++. Well, turns out that's kind of tricky. There's a couple reasons why you can't do that. The first one is inside of V8, when we're executing JavaScript code, we have an ABI. We have a sort of an interface, the way code calls each other inside of Java while executing JavaScript, that is different than the C++ ABI. And because they're different, it's really hard to interoperate without a bunch of extra machinery. Turns out that machinery is expensive enough from a performance perspective that it's really not a good idea to do that in most circumstances. There's also this thing called deferred code. If we have a built-in that has fast paths incorporated into it, for example, if you are iterating over something that's an array, you can pass, in the case of the reduce built-in, you could have passed it something that wasn't an array, and ECMAScript defines exactly what happens in that situation. But if it is an array, we know we can do that pretty fast and pretty quickly. We like to express this in our built-ins, where we have a fast path. We run some checks, and if those checks hold, we do the fast common code. Otherwise, we go somewhere else, do something much more expensive, and then jump back and resume where it makes sense. Right? So you have the inline fast path, outline slow path. Hard to do this in C++ because you actually literally want the fast path to be inline. You want to control how the compiler generates the code. Tough to do in C++. We also have a GC, a garbage collector, in V8. And one of the things we want to do is be able to have pointers that are not just to data structures on the C++ heap. We want to have pointers that are to objects. And because of our GC actually moves objects. It compacts, it moves them around for efficiency. It's important that we know where each one of those object pointers are and handle it specially in case there's a garbage collection. And it's really difficult to do that in C++. It's very difficult to sort of specify there's a pointer here, and it's going to be an object pointer, and no matter what happens, you have to tell me when you do anything with that pointer in the compiler, in the C++ compiler. It just doesn't work. You have to build an indirection. It gets really expensive. Doesn't work. Another thing we do built-ins is we do tail calling. It's sort of a variant of this deferred code. We'll inline the common case after doing some checks, and if we can't handle it at all, we'll then tail call out of the fast implementation into a C++ implementation that has all these disadvantages, but we don't care because it almost never happens. We just need the slow implementation to be spec compliant. Okay, so C++ isn't the right tool. How about we write everything in assembly language, right? That's fast. You have all that control. Turns out for a while we kind of did this, and we accumulated like 45,000 lines of assembly code per platform. We have like 9 of them. And as you can imagine, it sort of turned into a mess after a while because it's really hard to sort of express intent when writing assembly language. You can only express nuts and bolts. So it turns out that's not really a good idea either. So is there something we can do instead? Well, let's take the idea from the handwritten platform built-ins, these assembly ones that we had. They were really fast, but impossible to maintain. Is there something that we can sort of do that's better than that? It has all the advantages, but maybe is less complex, easier to manage? Well, turns out we can. So TurboFan, we have this compiler technology that has the ability to generate machine code, optimized machine code on 9 different platforms. And it has this intermediate representation that represents operations at a high level. Add these two 32-bit numbers, load this value out of memory, make this call to this function. And by exposing that interface in the right way, we can describe exactly what we want to do at almost an assembly level, but in a cross-platform way. And so the interface, or the component that does this, we call the code stub assembler, just to be really confusing. Because we call things sometimes stubs and sometimes built-ins, it's a mess. But anyway, we build built-ins with the code stub assembler. Okay, let's go down to sort of the check sheet, what this gives us. GC support. Turns out doing this in assembly language is really hard because you have the same problems as you would in C++. Somehow annotating things explicitly, this thing in this register at this time is an object. Wow, that gets really difficult to maintain. Turns out in the code stub assembler, when you create values and you manage them, part of the interface allows you to express, hey, this thing's going to be an object and it will be for its entire lifetime. Just do the right thing for me. And by the way, put it in a register if you can. Right? Do the right thing. So you get that for free. Register allocation. Sort of just mentioned that. One of my colleagues likes to call the handwritten assembly version of register allocation in-brain register allocation. Turns out it's really hard to do. You get it wrong all the time, and it creates almost impossible to find bugs. Because we have an optimizing compiler in TurboFan, if we use the backend for that, which has a register allocator, you don't have to grapple with these problems in writing stubs with the code stub assembler because the register allocation is done for you. It's done by machine and not in-brain. All those sort of impedance mismatches that I mentioned with the ABI, with calling back and forth between built-ins and JavaScript code, they're gone. If you write things by hand in assembly language, it's very difficult to maintain, very hard to do. In the CSA, you basically just create a descriptor and say, hey, I want to call this function, and it has this particular set of parameters, put these registers in the right place from these values or whatever. Just do the right thing, and it generates that code for you on 9 platforms, when you would have to do that by hand if you wrote them in assembly language. We have some pretty neat optimizations in the back end of all of our code generators. So we do instruction selection, which means on Intel platforms, we can sort of combine addressing modes, make them much more efficient. We have an instruction scheduler, which is something that's really hard to do by hand in assembly. our instruction scheduler creates a model of the, simplified model of the processor and figures out if I reorder some of these instructions, will you get faster code? Doing this at scale in assembly language, really hard. And last thing, there's tool integration. Turns out that the CSA, the code subassembler, can generate the right records that it associates with the code that it generates so that you can use the Linux perf integration to see where we're spending time inside of these built-ins. If you do that in assembly, you would have to build these records by hand, totally unmaintainable. So this is a great thing, right? With this code subassembler, we can now generate at scale for all of our platforms these built-ins that are customized for the functionality that we need. So how does this turn out at the end of the day? Well, so let's try that integer array again with Chrome 63, which just has the CSA version of the reduce built-in, right? So it has a customized version written with the CSA interface that generates pretty good assembly code for 9 platforms. So you run it the first time. Well, that's not great. There's still something going on here. No, I don't know where that C came from. Anyway. But for the string case, we're faster already. That's good. Why could this be the case? We'll get to that in a second. Yeah, because the C, that's right. So I'm not advising you to randomly add C code to your JavaScript. That was totally not on purpose. That was, no. Anyway, good news. Consistency. It's when you run the integer array through it again, it's consistent. There's a happy ending to the story, so bear with me. There's more we could do. What was going on? Why were we still slow for the integer array? Well, there's actually 2 things in play here. Remember that example I showed you originally with reduce? It calls this arrow function for each element that we have. So you can imagine as time goes on, we start by calling the reduce function. We spend some time in it, does some setup and some checking and whatever. And then it calls back the callback function to do the work, adds 2 numbers. And it goes back. And it goes back to the arrow function, adds 2 numbers, goes back. Yeah, right? So you get the idea here. I won't go through all of it, but it goes back and forth a bunch. So what's the problem? The problem is that calling back and forth between the reduce built-in, which is really fast now, but that arrow function has a lot of overhead. That overhead, if the work that you're doing inside of the arrow function, that plus operation is very small, the calling back and forth is actually much more expensive than the work that you do inside of the callback. So how do we solve this problem? Well, we have this optimizing compiler, TurboFan. And what we've done is we've taught TurboFan that when it sees a call to reduce, and it knows that the function that is called back meets certain criterion, and it's small enough, and the phase of the moon aligns, and it's the 3rd Tuesday of every month, that it can inline the operation. And it generates, when you send your code then to the optimizing compiler, it generates 1 piece of code for all of the reduce, including the inline version of the callback. So it looks more like this, right? So instead of calling back and forth, there's 1 chunk of optimized generated machine code that does both. You can probably, guess. One thing to add here. We talked about polymorphism being a bad thing. Turns out there's some tricks we can play in the optimizing compiler. By the time we get around to optimizing, we could have recorded that, by the way, at this place that you call reduce, it only ever gets called with an integer array. And it remembers that in the place in the code that you call reduce. So if you have one part of your code that does string operations with reduce, and another part of your code that does, it has integer arrays that it works on, those 2 things will be handled separately, and the type feedback will be separated in such a way that we can specialize and make it monomorphic for those call sites. All right, punchline time. So let's do it. Let's do the benchmark again. This time being inlined by TurboFan. Pretty good. Oh yeah, that's thanks, but anyway, let's do it for the string. Pretty good. Interesting to note here that it's actually faster than the integer array. Kind of makes sense. It's a smaller array. It should be doing less work. And running it again. Not perfect. Still pretty good. It's honest, right? It's still better than anything we saw before. So let's take a look at these numbers in comparison. The first one is, let's start out with the self-hosted built-in that we would have had in Chrome 58 and before. Using that test, the integer array first time, string array second time, and then the third test was integer array a second time. As a baseline, the self-hosted built-in is 1. So anything that gets faster than that is smaller, so smaller is better. The first thing you notice here is if you have a handwritten version, but you use it as a library, right? We had that handwritten sum function. If you use it in a bunch of different places, then it's great if you're monomorphic. The first time you call it, it's super, it's really fast. But you see it gets progressively worse as your code becomes more complex. That's not predictable baseline performance. Okay, with the CSA, monomorphic case is slower, but immediately in complex code, if you're dealing with strings or you're dealing with polymorphism, it's already faster than the self-hosted built-in and comparable, if not faster, than the version that's handwritten. And finally, if you use the TurboFan inlined version in Chrome 66 or later, you'll see that it's faster than any of them. It's faster than the handwritten version in the monomorphic case. Why? This is an important thing. Remember I told you we have this specialty knowledge because we read the spec and stuff. Turns out that if you look at the reduce function in the specification, it leaves out some of the steps that you might have to actually technically do to be correct if you use your handwritten loop. So we have opportunities to operate or to optimize that you may not have in handwritten code. So, important lesson learned here, express intent. The reason these built-ins, these higher order functions are there is to allow you to say what you want to do at a high level and let the compiler try to optimize it with your intent and not try to figure out what your intent was, like we did in the self-hosted built-ins, from the individual statements that were made. One really nice aspect of the reduce built-in and many other ones, actually at this point, Chrome 66 or later, Lodash. It's a great library that for a long time was the only way to get really good performance for some of the array built-ins. If you compare Lodash now against the latest version of V8 with Ignition and TurboFan and these inlining of the built-ins, it's much faster to use V8's built-ins and not the sort of these standard workaround solutions. That's great news. Okay, time for takeaways. Design minimally and specifically. This is a lesson we learned the very hard way. Don't over-optimize, prematurely optimize, or build complexity into something that you may never need. Write idiomatic JavaScript. Use the features that are provided with ES6 and new versions of the JavaScript language because they allow you to express your intent at a high level, which gives us more opportunity to optimize your code. Choose the right benchmarks, because those benchmarks will come around to haunt you if they're the wrong ones. Measure and tune carefully. Spend time actually creating a framework that measures the things that you care about so that you could do it iteratively and get better on the things you care about. That's it. Thank you very much.